Hi everybody, it's Mr. Molacash. This is our week 7 video for Math 171. Don't forget, if you need to contact me, here's my email address at Johnston. Sorry about my chicken scratch there. cc.edu. Okay, just going to check real quick to make sure that everything is looking good on the camera. So a couple of things this week. We're doing sections 1.6 and 1.7. So in 1.6, we're dealing with what's called transformations. I realize this marker is kind of thick, and I'm sorry about that if you can't see. But anyway, transformations. And so with transformations, you have the graph of a function, right? Let's say this is the graph of a function, right? Maybe that's y equals x squared, something like that. So there's a couple of things that you can do to the graph. You can reflect it, you can stretch it, you can move it left, right, up, or down. So this is what we call a parent graph. But what you can do with your parent graph is, like I said, you can do some different transformations. You can transform the way that the graph looks. So for example, if you had y equals negative x squared, that would take the graph and reflect the graph over the the x-axis. The reason being because what we're doing is you're taking all the y coordinates and making them the opposite. So all the positive y's now become negative. If you change x to the opposite, if you change x to be the opposite thing, like let's say the opposite of x squared, then what happens is all your positive x's become negative and all your negative x's become positive. So this graph gets flipped over the y-axis. That's a reflection over the y-axis. And of course this would look exactly the same. Later on we'll talk about this kind of graph that has y-axis symmetry. It's called an even function in section 1.7. All right, so what happens if we do, say y equals 2x squared? Well, then all the old y values get doubled. So, if when x is 1, y is 1 here, but when, what we'd have to do with the 1 here is multiplied by 2. So every y coordinate is going to be twice as far away from the x-axis, and so this kind of gets stretched out, right? If there was a 1/2, then it would be half the distance to the x-axis. All the y values would be cut in half, and it would be sort of compressed. I think that's the right way to describe that. Okay. All right. So that's what happens with stretching graphs or reflecting over the x or y axis. Now there is a number here that we call a, right? And with parabolas, the a tells us how stretched out it is, or whether it's reflected over the x-axis. Okay, so there's a couple other things we can do, right? We can take our graph, we can add to the x, or subtract rather from x, and then we can add to the whole y value, right? So h and k are the coordinates of the vertex. But what that has to do with the original graph is the role that h plays is that it moves the graph left and right. So here it's the opposite, right? H is the 0 of x minus h. So what you'll need to do is whatever is in here, you take the opposite for h. It's the opposite of the h in here, but it's the same as k. All right. So for example, if we had, y equals 1x squared again, but let's say we had x minus 2 squared plus 3. So what would happen to this graph is it would move right 2 and up 3 because the vertex is positive 2, 3. And again, this is positive because this is negative, but it's the same thing for the y value there. Okay, so everything would go to the right 2 units and up 3 units, and then you draw your same parabola. So that would be y equals x minus 2 squared plus 3. All right, so that's just a quick rundown of transforming graphs. There's a lot more to this in Alex this week and in your textbook. Remember, in the ebook, there are videos for every example, and I'm going to put a couple extra videos after this one, regarding what we're going to talk about soon. In fact, right now, the 1.7 section, right? So in 1.7, there's a lot of things going on, but the first thing is, what is an even function or an odd function? Okay, so there's a couple of ways to test this out. First of all, there's an algebraic way. There's an algebra way to do this. All right, so by definition, an even function is one where if you put negative x in, you get the same y value that you get when you put positive x in. Okay, geometrically speaking, or maybe I should just say graphically. I think graphically is probably a better way of saying this. Graphically, we could say f of x has y-axis symmetry. So for an example, y equals x squared is an even function. So you already saw earlier in the video that if we flip the graph over the y-axis, it's the same thing, right? But the problem here is, if you had to do this algebraically, okay, you'd have your original function. Now we're also going to say, okay, well, if I replace x with negative x, do I get the same thing? And the answer is yes, I do, because negative x times negative x is x squared. So we get the same thing with f of negative x that we do with f of positive x. They're the same exact expression. So that's an example of an even function. Okay? All right. And if I'm going really fast here, I apologize for that. My videos have been getting really long, and I'm trying to shorten them a little bit. So if I'm going too fast, just, you can pause, rewind, or whatever. That's the great thing about videos, right? Okay, so an odd function, well, let me say what that means algebraically, okay? So, and I'll abbreviate now. Algebraically, an odd function is a function where when you put negative x in the place of x, you get the opposite that you get with the original y value, okay? So when x's are opposite, the y's are opposite. That's another way of thinking about that. So graphically, this has what's called origin symmetry. And I'll explain what that is. So let me just kind of flip this over. If we graphed, y equals x cubed, right? So let me put some points on here for y equals x cubed. So something that looks like this. And then see, like -2, -8 is on this graph. So something that looks like this, right? Okay, so, here's x, and here's f of x, right? So whatever x value, you get a y value. Well, if you put in the opposite of that x, you get the y value for that, right? But it's also the exact opposite of this. Okay, so that's another way of thinking about it. Another graphical way of trying to figure this out with origin symmetry is you can kind of anchor down the origin, and if you take your graph and you rotate it around the origin 180 degrees, you get the same exact graph. So that's a real quick test for origin symmetries. If you can do that to a function's graph, then it means that the graph came from an odd function. Okay, it came from an odd function. So, so for an example, this is y equals x cubed, right? If you try putting negative x in, okay, Well, what happens when you do negative times a negative times another negative? You get negative, right? And then x times x times x is x cubed. And you can see that these two things are not the same, they're opposite, right? So those are odd, that's an odd function, and the original function's an odd function because you get the opposite thing from the original when you put negative x in. Okay. All right, so our next piece of information that we need to talk about is what is a piecewise function. Wow. Okay, these are not necessarily everyone's favorite thing. And I'm going to put some more information about piecewise functions from Patrick JMT in this week's assignment folder. But an example of a piecewise function, just very quickly, as like an overview, is a function that's defined in pieces with a curly brace like this. So let's say that we have x squared when x is greater than 0, but we'll have x when x is either 0 or less than 0. Okay, so there's different pieces going on, right? So the top piece is going to be allowed to be used when x is a positive number. So, for example, if I wanted to find f of 5, I would use the top piece to do that. I would do 5 squared, and that's 25, right? But anything that's not a positive number, namely 0 or negative, right? If I wanted to say, what's f of 0, I get 0 because I put it here. Not because of the top. I have to use the bottom because that's where x could be 0, right? Okay, so let me give you a little test here while you're watching this. Let's say that we wanted to do f of negative 3. What would that be? Okay, the answer to this would be negative 3. And the reason is because we would use this piece of the function because negative 3 is less than 0. So we would put it here instead of squaring it. Okay. You can graph a piecewise function. In fact, I'm going to graph this on the back here. So we'll get rid of our x cubed graph. So when x is squared, you remember earlier in the video, the parabola, the standard parabola looks like this, right? But I'm only drawing it on the right side because I want x to be greater than or equal to 0. So here we're going to use the rule f of x is x squared, right? But I'm going to use the y equals x, which is a slanted line that goes through the origin at a 45-degree angle. I'm going to use that line over here when x is strictly less than 0. And I think I got these backwards. Sorry about that. It turns out it doesn't matter, and I'll explain why in a moment. But okay, so when x is negative or 0, we get a line. When x is positive, we get the right-hand branch of the parabola. So why doesn't it matter where I put the equality? Because if I put 0 here, I get 0. If I put 0 here, I also get 0. So these two parts, these two pieces run into each other. It's not always the case that the pieces run into each other. They could be separated. There could be a break in the graph. And if you go on and take calculus 1, you have to kind of delve into whether graphs are continuous or not in a much more formal way. But that's an example of a piecewise function and how to graph one and how to evaluate it. Okay, there is one last thing that I want to talk about, and that is something called the step function. It can also be called the greatest integer function, so it looks like this. And things like this are useful, like say at the post office, up to, let's say, not this function. Well, let's just say we want postage, the postage stamps, right? So, let's say up into if 0 is anything that weighs anything but less than 16 ounces, you have to pay 49 cents for postage, right? But after that, if x is greater than 16, then you have to pay more. You know, you have to pay like 74 cents, or let's say that, you know, if it's 2 pounds, you might have to pay $2.09, and then there's you know, different options after that. So, you know, if you were to graph this between 0 and 16, you'd have the same exact price, but let's say it's 16 or more, then, you know, you'd have a bigger price, and then if it's after that, it's a bigger price. So the reason why they call this a step function is because there's different, well, they look like stair steps, but you're stepping up to a new you know, function, and this is definitely piecewise. You can think of it in those terms, right? Piecewise. So the easiest one of these step functions is called the greatest integer function, and it looks like this. It has these crazy brackets that go around it, and this is defined to be the greatest integer. Greatest integer. So you have to stop and think, what is an integer, right? The positive and negative numbers that are whole numbers except all the opposites, and then 0, right? No fractions, decimals, or anything like that. Greatest integer that's less than or equal to x. So let's do a couple of examples. Let's say that we have to find f of 2.5. Okay, what is that? So you look at all the integers on your number line, right? You have, of course, 0, 1, 2, 3, 4. And 2.5 is about right here, right? So what is the biggest number that you run into that's less than or equal to x? The answer to that is 2. The answer to that is 2. Well, what if we did 2.9? Well, it would still be 2 because you haven't gotten to 3 yet. So the biggest integer that you can get to before 2.9 is 2. But it could be equal to. So, you know, what if we put 3 there? Well, once we hit x equals 3, then we've hit the integer 3, so the answer is 3. Okay? So that's the greatest integer function. That's kind of how that works out. The graph of the greatest integer function, I'll put that before we part ways this week, but the graph of the greatest integer function, as soon as you hit an integer moving from left to right, you have a closed dot, and then you end with an open dot and then move up. So it kind of like looks like this. And oddly enough, the domain of these functions is all real numbers. So you can put any number you want in, okay, and it keeps going both directions, right? It goes on forever in both directions. But, you know, you can put any number in, right? So, you know, if you want the greatest integer for 2.5, for example, you get 2 because here's, let's see, 1, 2, there's 2.5, and you get 2. You know, 2.9 would be 2. 2.99999 would be 2 for the y value. But once you hit 3, then you move up to that dot. Okay, so I hope that helps you out to understand the greatest integer function. But do recommend that you use the discussion board. You know, ask me questions in the discussion board if you think it's an appropriate question for the whole class, and I'll be checking that this week. And then again, here's my email address. If you happen to stumble across this on Facebook and you email me and you're not one of my students, I might not answer you. It just depends on if I have time. But I hope you enjoyed this video and that you have a great week. Thanks.